welcome you to another statistical topic. And of course, today, the focus is going to be on random sample and statistic. You know, when I say statistic, that is not statistics, that is statistic. Okay. So, what is the purpose of what we want to do today? Of course, today I'm actually going to walk you through some notations and of course the essence of the notations in real life. And of course, I'm going to tell you um, a little bit of the historical background, the reason why we actually need to study random sample and statistic. And let's get started. I need you to follow the way I'm actually going to, I'm going to be narrative in a way. Now, you know, we find ourselves in a world, where we actually um, want to understand our environment. We want to understand our political environment or economic environment and so on like that. And let me tell you this. Let's say we want to know what is the proportions of citizens that approve the job the president is doing. Of course, that is actually going to be called parameter, proportion now. So what we're looking for, okay, a parameter is a population characteristic value, okay, population characteristic, okay, value, okay, that we seek to determine. So we want to know the proportion of citizens approve the job the president is doing. We may also want to know what is the average household income in a particular country annually. We may want to know what is the proportions of females in Canadian Parliament, what is the proportion of female in US Congress. You know, there's a lot of things that we may want to know about. Now, if we want to, so whatever we want to know that we're seeking to know about is what we call parameter. And you know what? If we want to, because the parameter is a population characteristic value, we need to go to population. But let me tell you this. We cannot obtain parameter directly. The only way we can obtain parameter directly is when you study everybody in the population. Okay, we don't have resources to do that. Okay, we're limited by budget, we're limited by time. Okay, and that is the reason why we normally take a sample from the population. Now, taking a sample from the population, okay, and of everybody knows, sample is not the same as population. If a sample is as big as this, if a population, let's say this is population now, okay, the sample we're going to choose is just going to be small. Okay, this is good. This is what we call sample. Now, this is what happened. The way we're going to choose this sample matters a lot. You know, if I want to choose a sample from the population, then I actually going to use what I call the principle of randomization. And that is why you can see in the title, random sample. Okay, so which means we give equal chance, we give equal probability to every element in the population. Okay, so the moment you find yourself in the sample, then it means you were randomly choosing from the population, because when samples are randomly choosing from population, of course, there is tendency what you choose is going to be a good representative of the population. Okay, now you understand what I mean by random sample now, right? Okay, now when I have a random sample, what am I looking for? I'm looking for parameter, but I'm not going to get parameter with sample. I'm only going to get parameter with population. So what I'm going to do is, what I'm going to compute from here is what we call statistic. So statistic is a numerical summary of sample, while parameter is a numerical summary of the population. I'm going to say that again. Statistic is a numerical, numerical summary. Okay. Statistic is a numerical summary of the sample. For instance, I'm working on income. If I'm working on income, this is my population, Y1, Y2 up to YN. Maybe the size of the population, I'm talking about United States population now, for example, maybe around 350 million. And let me tell you this, if I'm talking about income, let me just say those, because it's not going to be everybody that is working in the United States. Don't forget, we got children, right? Let's just say the working population, I'm just assuming, let's just assume 100 million. Okay. Now, from here now, I choose a sample. Maybe the sample I'm going to choose at the end of the day, maybe 1,000. Okay. And in that very sample, I'm going to have Y1, Y2 up to YN. So the Y here is a random variable in the sample. This is a random variable in the population. The Y1 here is somebody with a particular income in the population, somebody with a particular income in the sample. So when you take a look at what we're doing, like I used to tell students, theory of statistics, mathematics is very easy, but the moment you understand what is behind notations, what is behind equation, you're actually going to be fine. Now I want to go into that. Now you understand what we mean by random experiment. You understand what we mean by statistic. Like if I compute, maybe I'm looking for the average income. If I compute my average from here, that's a statistic. Maybe I'm looking for the proportions of Americans who approve the job the president is doing. If these are, the people in the population in the United States, and I choose a sample, now, each of these, I'm actually going to have 1, 0, 1, 0. 1 is going to be, don't forget when we are dealing with two possible outcomes, we're going to label one as 1. We're going to label the other one as 0. 1 means yes, I approve the job the president is doing. 0 means no, I do not approve the job the president is doing, which means based on the sample, I can also compute proportion. Okay, all of that, whatever I compute from sample is what we call statistic. And let me tell you this, why do we compute statistic? Okay, if everything is nice, we're actually going to use the statistic value that we got to represent the parameter we were looking for in the first place. Okay, that is our intention, and that's what we call statistical inference. Statistical inference is making a judgment about a whole based on a particular. That's what I mean. Okay, now take a look at this. We are interested in the following scenario now. Okay, we have an experiment that produces a random variable y. This is an experiment. I have a random variable y, y1, y2 up to yn. Okay, and let me tell you this. Every random variable has a probability distribution. What do I mean by that? If you take a look at this guy, some people that are earning certain income value, okay, what is the number of them in the population? That will be the frequency of that, which means every element in the population here, okay, they have their corresponding probability. What we mean by that is just like the numbers of time they occur in the population. That's what it means. Okay, now when we're dealing with a random variable y, the probability distribution we're talking about could be discrete form, it could be continuous form. When it is discrete form, of course, that's going to be PMY. Give me 1 second. When it is, I think I'm going to use, let me use my pen now. See. Okay, so take a look at this guy. Okay, so PY, the PMF, when it is discrete, when it is continuous, it's going to be called PDF, which is called probability density function. And we're going to use f of y to denote the probability function of a continuous random variable. Now, when we are conducting an experiment, now take a look at this. When I come here to take a sample, then I'm conducting an experiment. And if I take a sample and I ask them question, okay, then I'm actually going to have an outcome. Okay, experiment actually produces, it's a trial that generates an outcome. Okay, so now if the experiment is repeated n times, the n times is going to be the sample size. How many individuals did I actually sample at random? That's what it means. That's what we call the repeated. The outcomes of the repetition are independent of each other. Now take a look at this. Independent, because that is the fundamental requirement in statistics. If I want to use statistic to represent parameter, then the way I'm going to choose this guy, I'm going to choose them in a way that they are independent of one another. Does that make sense? Okay, so we are assuming independent. Take a look at this guy now. And that was why we said y1, y2, up to yn. IID means independently and identically distributed. What do I mean by IID? Independently means what this guy is going to tell me is going to be independent of what the other guy is going to tell me. Don't forget, I choose them at random. Okay. Then identically distributed means they came from the same population. Any question? That's what we mean by identically distributed. They are from the same population. Okay. Now, and of course, take a look at that. They could follow a probability distribution. That could be a discrete type. If it is discrete type, you actually going to have a P. When it is a continuous type, it's going to be F of something. Does that make sense? Okay. Now, whether we're dealing with a discrete type or we're dealing with a continuous type, and we actually assume that y1 up to yn are independent, then we can use the probability formula. We can use probability assumptions. Now, the probability assumption is actually going to tell us, when events are independent. If I have two events, A and B, they are independent. The probability of the joint occurrence of A and B can be written. Of course, I can write that as the product. Take a look at this. The probability of A intersection B is going to be probability of A multiplied by probability of B. This is from fundamental law of probability. If A and B are events and they are independent. But right now, we're not talking about events. In statistical theory, we use random variable to represent events. Don't forget. Now, we now want to talk about y1, y2, up to yn independent. Then we're now going to be talking about the probability of the joint occurrence. Now, the probability of the joint occurrence, oh my God, take a look at this guy now. The probability of the joint occurrence means, what is the probability of the joint occurrence of y1, y2, up to yn? Because y1 up to yn are independent using the multiplication rule of independence. I'm actually going to multiply the correct, the probability of y1 by probability of y2 up to yn. And if I want to write that in short form, I'm actually going to just write that. I'm going to write a pi. I start from 1 to n. P of yi, that is a shorter way to write the probability of y1, y2 up to yn. Okay, and I'm using P in that situation, assuming that the probability distribution is discrete. What of in a situation where it is continuous? Okay, it's still going to be the same, except that instead of me to be using P, I'm actually going to be using F. Is there any question on this page before I move to the next page? Is there any question? Okay, now I'm going to go to the next question now. I'm going to go to the next page now. Now, so the theorem is just that this is the theorem, independence, that I just talked about for PMF, okay, PMF for discrete random variable and PDF for continuous. Now, I want us to go into an example right now. Okay, I want us to go into an example right now. Okay, and we want to focus on this guy. We want to perform an experiment. We want to perform an experiment with a die. Okay, or just like what I used to say, we live in stochastic environment. We live in a probability space. If we want to perform an experiment in a in that kind of environment, we need the knowledge of possibility, which I call the sample space. Now I'm working with a die. How many sides do I have in a die? 1, 2, 3, 4, 5, 6. Oh, there are six sides in a die. Oh, I'm working with a coin. How many coin? How many sides do we have in a coin? Oh, 2. Oh, head and tail. So you need to be able to understand the possibility, okay, the cardinality of the sample space. Okay, now I roll a balanced die 10 times. Okay, why do I call it balance? I call it balance in the sense that it has to be 1, 2, 3, 4, 5, 6. The moment it is 1, 2, 2, 4, 5, 6, this is no longer a balanced die. Okay, because we expect the sample space to contain elements that are distinct. Okay, now I roll a die 10 times. Okay, irrespective of the numbers of time I roll a die, the probability of any size showing up is 1 out of 6. What am I assuming? I'm assuming a classical approach in probability. Okay, now and if I toss it 10 times, then I'm actually going to have y1, y2, y3 until I get to y10, because I toss it 10 times. And why am I having 1, 1, 1? Okay, don't forget, before you go out, maybe you have something in mind. Okay, maybe I'm looking for 6. Okay, when I see 6, maybe I'm going to call it 1. If I don't see 6, maybe I'm going to call it 0. Okay, now, and that is the reason why you see the probability of y1 equal to 1, y2 equal to 1, y whatever equal is actually still going to be 1 over 6. So using the law of independence, it's going to be 1 over 6 times 1 over 6 times 1 over 6. And because we have the same probability, I can just do 1 over 6 raised to power n, where n is going to be the numbers of times it is toes. So tossing it 10 times is going to be 1 over 6 raised to power 10, and which is mathematically going to be 1 over 6 raised to power 10. So that is for this guy. Okay, now, and that 1 over 6 raised to power 10 is the probability of the joint occurrence of y1 up to y10. Now, I want to go, and another thing I'm going to tell you here, computing that, we did not have any probability distribution in mind. What if in a situation where we now say, okay, take a look at the next example. Okay, suppose that y1 up to yn, let's say we have a random sample of y1 up to yn that follows exponential distribution. Remember the other time, exponential distribution, I think when I was revealing with you, exponential distribution, if I have I follow exponential with parameter beta, of course, my f of s is going to be 1 over this raised to power, or let me be using y, sorry. So y over beta, then I'm actually going to have y greater than 0, beta greater than 0. But right now, they give you exponential in parentheses 1, which means, the beta is already equal to 1. If I plug in beta to be 1, okay, I'm actually going to have a special form of exponential distribution that's just going to be exponential raised to power minus y. Okay, so which means, for any variable, for whether y1 or y2 or yn, you take a look at this guy now. Give me 1 second. I want to see. Is it my phone or whose phone is oh, okay. Sorry about that. So now that was why we got this, because we're using this guy and they already said beta equal to 1. The parameter of the distribution is already known to be 1. So plugging that in, we actually have that guy. Now, if f of y I equal to that, it means, you know what that means? Since y1, y2, up to yn are identically distributed, then it means f of y1 is going to be this guy. F of y2 is going to be this guy. So why am I writing that? Because that is because of the IID. They're identically distributed. Now, if I now want to get the probability of the joint in that situation, so what I'm just going to do is to apply this. Take a look at that. Okay, f of y1 times that, then I'm just going to have this guy. Take a look at that. Then that is going to give me the probability of the joint occurrence. Now, the example that I cited right now is a situation where you know the underlying probability distribution. Okay, now I want to go to something more. I want to go into another example. Take a look at this guy. I want to talk about household income of a particular nation. Okay, now the household income of a particular nation will follow a distribution. Okay, the distribution may be known or may be unknown. Okay, now, and when we're talking about income, okay, the appropriate probability will fall under the probability density function. Okay, because income is not discrete. Okay, so and that was why you can see here I'm already assuming f of y. Okay, whenever you see f of y, I'm actually saying the probability distribution is continuous. That means the random variable is continuous, and I'm using PDF. Now, let me tell you this. We want to know the average household income. The true values of the average household income is expected value of y. That is the true value. Okay, that's a population mean. Population mean is different from sample mean. Before we go into experiments, okay, we already we have a formula. If we know the probability distribution, okay, the moment and if the probability distribution is of continuous type, of course, if I want to get my expected value of y is going to be the integral y, f of y dy. Okay, but let me tell you this. Suppose, okay, now suppose we don't know the exact form of f of y. Let me tell you this. In a very realistic situation, we may not know the probability distribution of the characteristics of interest. And we still want to have an estimate of the income, of the average income. Now, so in that situation, we cannot obtain this guy exactly. Don't forget, this guy is a parameter. I told you the other time, mu. This is a parameter. So what are we going to do? We're going to estimate. Okay, and you know what? How do we estimate? Then we should be ready to take a sample. Okay, the statistic is the same thing as estimate. Does that make sense? So that is what we want to do now, and because of that, we're going to conduct a survey. That's why most of the time we conduct a survey. Okay, then we randomly draw n household. Okay, randomly. I'm not going to draw my household because it's my household. It has to be random. If I'm doing that in Anoka County, I live in Anoka County, so I have to draw the household, giving equal chance, equal probability to all the household. Now, then I'm going to record their income. Oh, Y1, that's going to be the income of this household. Y2, that is going to be the income of this household. Okay. So, like I said, this is a sample, Y1, Y2, up to YN. Oh, the income of this household, the income of another household, and so on like that. That is Y1 up to YN. We record that. Then we're going to assume they are independent. Okay. The income is independent, even though they work in the same place, because there's possibility. They could sample an household here and another household, and the people living there, maybe one or two are working in the same place. It doesn't matter. Okay. Now, they are independent, and marginally each of them has a PDF. What do I mean by that? Each of them has a PDF. Oh, what I mean is, if this guy report 50,000, okay, this guy has a corresponding F of Y1, which is going to be the numbers of time these 50,000 occur. That's frequency. Probability is not, when people hear probability, they're going to be scared. No, probability is talking about how many times does it occur. That's what it means out of generality. Okay, now, then Y1 up to YN is a random sample of the population. Then how do we now find the probability of the joint occurrence of all of that? Then I'm just going to multiply, the marginal, we call that marginal probability, which is going to be the probability function for each random variable. Okay. Now this is the situation. If I want to for instance, I want to estimate mean, okay, household income, then I need a formula in my head. That very formula is what we now want to talk about. That formula is called estimator. That's an estimator. There's a difference between estimator and estimate. Estimator is a formula or method used in estimation process. When I say estimation process, you're using that on sample. Okay. Then estimate is the value that you got. If an estimator is wrong, an estimate will be wrong. But let me tell you, in statistics, we're going to focus more in this course on estimator. Okay. How good is our formula? Because when the formula is wrong, when the method is wrong, then the estimate is going to be wrong. Now, take a look at this. Now, a common estimator of mu is a sample average. But let me tell you this. There are other estimator for sample average, like median, mode, because there are three measures of central tendency, or we also call them three measures of location: mean, median, mode. We got situations where we use them, but the most common one is the mean. Okay. Now take a look at that. Y bar equal 1 over n summation yi, which means I'm actually going to sum y1, y2 up to yn in my sample divided by the number. Okay, now, but take a look at this. The y bar is random. Why is it random? Oh, it is random because if I give you an assignment in this class and I say, okay, you know what? I need you to investigate in this university how much on average students spend per week. And I give you the research. I say, okay, you're gonna go into University of Minnesota, select randomly 50 students. The participants in your sample is going to be different from the one in the sample. Is going to be different. Everyone is going to have different individuals because you are sampling at random. When you have different individuals, then you're actually going to have different means. Does that make sense? Now, it's now when something varies, when your mean varies, your average is different from this guy average, different from my average, then that is variation. Then randomness thrives in variation. When something varies, then it is random. And that is why Y bar is random. It's random because you know, you can get different value from mean. Don't forget, when you go into the population, even though you are working on the same thing, even though you have the same sample size, you are not going to get the same results. And that is why it is random. It varies. And that is the reason why at times when you listen to news, and maybe you listen on about maybe on election, when you, like in the United States, when you listen, maybe you watch CNN, you watch Fox News, you watch MSBC, and they have a poll on on a particular candidate. They're actually going to have different results. They will report different results. Why? Because they have a different participant in their sample. Okay, now, so which means Y bar is a random variable. Okay, now take a look at, we want to talk about population and random sample. Population is unobservable. Why is it unobservable? Because you cannot examine every element in the population. We do not have resources for that. That's why we say unobservable. Why sample is observable? Okay, that's one you're going to work with, right? Okay, and of course, for population, we're going to have either a PMF or PDF, okay, as a probability distribution. Then there's going to be parameter, okay? Now, what to replace parameter in the sample is the statistic, okay? What replace, if parameter to the population, statistic to the sample. And don't forget, statistics serve as an estimator for the unknown parameter. Okay? And now let us compare the average in the two. Population mean is different from sample mean. Take a look at this. This is if the distribution, if the random variable is continuous, this is the way I'm going to get a population mean that we call the expected value of Y. But for sample, the only way I'm going to get the sample mean is to use this guy here. Do you see the difference? It's to use this guy here. Okay, so one is called sample mean, the other one is called population mean. But let me tell you this. They are never going to be the same because of the fact model is not the same as reality. But you know what? We actually want to put necessary machinery in place to ensure the closeness of the sample mean to the population mean. Okay, so I think I gave you so statistic is a numerical summary of the sample. We also call it a function of the observable random variable in a simple and known constant. And of course, because of the fact our statistic varies, if I ask you to find the mean, go to the population, take a sample randomly, your mean will be different from my mean. Not only that, if I ask you to obtain proportion, you're also going to have different results. If I ask you to find the minimum from data point, your minimum may not be my minimum. Okay, minimum statistic is also a statistic. Then if you want to talk about the maximum, you want to talk about the range, they are all statistic and they varies. Now, anything that varies, okay, we can talk about the distribution of it. And that's why you see the distribution of statistic is called sampling distribution. Okay, sampling distribution. Okay, going to give you some example. Want to go into another example right now because of my time. Take a look at this guy. Y1, Y up to YN follow normal distribution. Okay, there are two parameters in normal distribution. Mu and sigma square. At times, mu may be known, variance may be unknown, and at times the two of them may be unknown, and at times the two of them may be known. And you are told where mu and sigma square are unknown, okay, mean and sigma square are unknown, which of the following can we call statistics? Okay, so you can take a look at that. But if you really want to know what statistic is, okay, statistic is something that varies. Okay, when I compute mine and when you compute yours, we're actually going to get different value. Okay, now I think I've explained. Okay, now going back to the example on balanced die. A balanced die is toast 3 times and recorded as y1, y2, y3. What is the sampling distribution of y bar? Why are we interested in distribution of y bar? Because y bar is a random variable. It could vary from sample to sample. My mean, when I toast it, when I toast die 3 times, my average will be different from your average when you toast it 3 times as well. Okay, now because of that, we're actually going to use the idea of independence. It's going to come on. That's what you see here, right? The probability of y1, y2, y3 is going to be equal to that, and we can actually multiply each of that. Now, this is the scenario. This is like, let's say the way it's going to play out. y1, y2, y3. This is giving you possibility. I may say 1, 1, 1. 1 in first occasion, 1 in second occasion, 1 in third occasion, or it's going to be 1, 1, 2, or 66. You know, I'm just listing possibility. There's a lot. Okay. Now, and in each, now, do you now see why I said mean is a random variable? Take a look at that. There's possibility. I toss the coin 3 times. I'm likely going to see 1, 1, 1, 1. My mean is going to be 1 plus 1 plus 1 divided by 3. Your own mean, maybe by the time you toss your own, it's going to be 1, 1, 2, and your mean is 4 over 3. Oh my God, we got different means. Take a look at that. Because of that, y bar mean here is a random variable because it varies. Okay, now, but let me tell you this. If it varies, we may want to focus on finding probability associated with a mean. Okay, now, and this is what we're going to do. Before of us going to use an underlying knowledge of die, take a look at this that you've done before in 4101. What is the possibility? How many side? 1, 2, 3, 4, 5, 6. What is the probability of 1 showing up, 2 showing up, or 1 over 6? I can find the expected value of y. Of course, if you want to find the expected value of y, this is discrete, it's going to be distance this, distance that, then you add them up, right? And when you add them up, that will give you expected value of y. But let me tell you this. Expected value of y1 is the same thing as expected value of y2. Is the same thing as expected value of y3. And if you want to find the variance, of course, finding the variance, okay, the variance of y is expected value of y squared minus expected value of y all squared. And of course, expected value of y squared is good. Summation this p of y. Y start from 1 to 3. Okay, you've done that before in 410 1. And of course, the variance of y1 is the variance of y2 is the variance of y3. Why do they have the same mean? Why do they have the same variances? Because the variables involved are identically distributed and they are independent. And they're also going to have the same standard deviation. Why am I having y1, y2, y3? Don't forget, you were told that it's those 3 times. Now, if I understand the expected value of y, if I understand the expected value of y, and I understand the variance of y, can I also obtain expected value of y bar? This is what I'm trying to say. If I understand the expected value of y, okay, I understand the expected value of y, can I obtain the expected value of y bar? If I understand the variance of y, can I also get the variance of y bar? If I understand the standard deviation of y, can I also understand the standard deviation of y bar? But let me tell you this. No matter what, this is going to be equal. Now, if the variance of y is sigma squared, the variance of y bar will be sigma squared over n. So these are not the same. And of course, the standard deviation here, if this is sigma, okay, this guy is going to be the square root of this guy, which is going to be sigma over root n. Take a look at that. Okay, and that is the knowledge. That's what we want to use here. Now, and that was why I take a look at this. I want to find the expected value of y bar. So this guy here, give me 1 second. No. Okay. This guy here is to be able to tell the world expected value of y bar is going to be the same thing as the value of y. Let's see. Use expectation to multiply that. It's going to have expected value of y1 plus expected value of y2 plus expected value of y3, right? And don't forget, I said what? They are all equal, right? So if they are all equal, then it just means I got 3 of that divided by 3, then it's still going to give me expected value of y. Then what about the variance of y bar? You know, when you take a look at this guy here, the constant is 3. You're gonna bring it out. That's gonna be 1 over 3 squared. Okay. When you have 1 over 3 squared, then you're gonna have the variance of y1 plus variance of y2 plus variance of y3. Why is it that there's no covariance? Can somebody tell me? Go ahead. Because they are independent. Send me a message for extra credit. My examination starts now in the class. Do you know you can hand extra credit, a lot of that before exam? And you can advise me on how you want to spend the extra credit at the end of the day. So y1, y2 up to yn are independent. So here, I'm only going to have variance of y because they are all the same. Okay, then it's just going to be three variance. Okay, and 3 divided by 9, that's going to be 1 over 3. That's going to be variance of y over 3. Look at this is general formula. Variance divided by n, where n is 3. So which means you'll be able to get expected value of y bar, the variance of y bar, then the standard deviation of y bar. Because if I want to make an inference on y bar, making an inference on y bar is, maybe I want to find probability associated with y bar, then I need the mean of y bar. I need a standard deviation of y bar. And the only way to get the mean of y bar, the standard deviation of y bar, is to first retrace your step. Understand what is the expected value of y. Now, the moment you know the expected value of y is automatically going to be expected value of y bar. Then if I want to know the variance of y bar, what is the variance of y? Okay, so that is that. And take a look at the rule here. I needed to take a look at the general rule. Recall this guy. Expectation, you remember last time we talked about linear combination. Okay, when I have a summation ai, yi, a1, y1 plus a2, y2 plus a3, y3 until you get to an, yn. Okay, now at the end of the day, it's going to be a summation. You know, the a is a constant. The a is going to come out. Okay, you see, the a is going to come out. Then expectation will attract a random variable y. And that is going to be summation ai expected value of yi. Then what about the covariance yi, yj? Covariance yi, ij equal to 0 in a situation where yi and yj are independent. Okay, then the variance of a sum of the linear combination now is going to be summation ai squared. Why do we have ai squared? Because it's a constant. Then the variance of y. Okay, so I think you can see that now. So the moment I understand the expected value of y bar, take a look at this. This is y bar. It's a random variable. Why? Because when I ask you to go into the university, work on how much students spend on average in a week. Take a random sample of 50 randomly. Your Y bar is different from my Y bar. You're all going to have different value for the mean. Because of that, mean is a random variable. It varies. And when something varies, I can find the mean of the means. Expectation of Y bar means mean of the means. The variance of Y bar means you want to find the, you are interested in the variance for the Y bar because Y bar varies. And the moment I understand I understand all of this, then I can find probability associated with a random variable. The bottom line is, if I want to find probability associated with a random variable, then I need to know, irrespective of the distribution, I need to know what is the expectation of the random variable and what is the variance of the random variable and what is the standard deviation of the random variable. The moment I have that kind of knowledge, then I'll be able to conduct whatever statistical inference with it. Okay, so that is how that is. Oh my God. Oh, this party want to end. Okay, that's going to be the end of the party. Is there any question before I go? Any question? How I got what? Expected value of Y bar? This one? Oh, the variance of Y bar. Okay, that 3 at the bottom is a constant. So it's going to come out. Take a look at this. So variance y1 plus y2 plus y3 divided by 3, right? Now, if we want to rewrite this, it's going to look like, if I want to write in form of linear combination, it's just going to be this, 1 over 3, 1 over 3. Here they are equally weighted. So this is more or less like A1, A2, A3. And because they are common, I can bring it out. Okay, 1 over 3, then I'm going to do 1 over 3 squared variance of y1 plus y2 plus y3. Now, if I have that, then I'm going to have, take a look at this, 1 over 9 variance of y1, variance of y2, variance of y3. Okay? And I told you the other time, they're all going to be the same. So variance of y1 equal variance of y2 equal variance of y3 equal variance of y. So if they are all the same, it's going to be 1 over 9, 3 variance of y. Because they are all the same. What do you have? Variance of y over 3. And what is the generalization? The generalization here is going to be the variance of, so the variance of y bar is going to be variance of y divided by n. So the variance of y is this guy here, n. It means n equal to 3. So if you don't want to go through all this process, all what you just need is, variance of y bar is the variance of y over n. Does that make sense? Do you understand it now? Okay, super cool. Any other question? Make sure you all stay safe and have a beautiful day. See you on Friday. Bye for now.